Okay, well, let's get started. So for the final part of the first day of Pastoral Fest, we're going to have a couple of tutorials, and then we're going to have open office hours. So the first tutorial is given by Ben Clifford, who's going to talk about dependencies beyond the DAG.
Right. Okay. So this is structured as a Jupyter notebook, which I've also put online with the intention of people being able to work through. So you're going to see a lot of this text, which I'm not expecting you to read now. That's for anyone reading this offline. So I'm going to initialize parcel first. Boop. Okay, so I'm going to talk about dependencies in parcel. I'm going to define quite a few applications in this tutorial. They're all going to be really stupid and simple. So for example, this one called first, which just returns the number 10 and pretends to do some computing and output some log lines. The actual models that most of what I'm going to talk about here today are based on real dependency shapes and problems that the LSST workflow that Tom Glansman talked about earlier has. So I'll just very briefly go through simple dependencies. If I can define an application like this called first, when I invoke it, what comes back is not the number 10. What comes back is a future straight away, and then it's going to sleep for a little while and run in the background. And once it's run in the background, I can ask that future, are you done? And do you have a result? And the answer is true. And that's where the 10 comes out of. So I can make another one called double. This one takes a parameter and we can double it. If I run that, pretty straightforward. So there's in this bit here, what's coming back is the future, and then I'm asking the future to give me the result, and that's where we get the doubled result from. So all of the parcel dependency handling is handled by connecting things together with futures like this. So I can take first, which is going to return 10, and I can double it. So here's a mini workflow specified using Python syntax. So it's a directed graph. We're going to run this, then we're going to run this, and we're going to get the result. And it should be 20, I think. Whoop. Hold the tension. There we go. Okay, so none of that is anything that you couldn't do in regular Python without parcel at all, which it just looks like we're invoking a function, passing the result into another function. But actually, because these are parcel apps, there's a future involved sort of in this little gap here. Where things start diverging is if we do more complicated things. So here's a function I'm going to use quite a lot, which just takes a whole list of arguments and it adds up those arguments and gives me the sum. So I'm going to use this quite a lot in this talk. So if I add 1, 10, and 2, I get a future. I ask the future for the result. It's 13. Okay, so here I'm going to say I've got a 3-node workflow. I'm going to run first. I'm going to run another first. I'm going to feed those 2 results into total. If I was going to run this just as regular Python code, what would happen is this first would run to completion, then this first would run to completion, and then total would run. But actually in Parcel, what happens is both of the first run at the same time, and hopefully they'll both finish around the same time. And so that's sort of one of the core things of using dependencies in Parcel, is to express that ordering of execution that isn't just a sequence of execution, of a linear sequence of steps. Okay, so Parcel can figure out that it needs to run, or that it can run these 2 firsts in parallel. The other thing to notice is this future came back. If I run this fast, the future that comes from executing total, we get that right away. We don't have to wait for any of the dependencies to run. The very last node of the workflow, we have a future to represent that completion straight away without any delay. And that's something that's pretty important. If you imagine that these apps, instead of taking 5 seconds to run, they're science applications which take a day to run, for example, suddenly the fact that these 2 can run together is 2 days worth of time condensed into 1 day worth of time. Okay. So if we go down here, I could write things in a slightly different way. And I'm going to claim that this is an extremely bad style. So I can call first twice and get the futures. That'll run nice and fast. Then I can wait for the results and wait for the results. And so A and B here will be the actual integers 10. They won't be futures. And I can pass those integers into total. And if I run that, it kind of looks like it's behaving the same, right? Hopefully. There we go. We get the same results. We've got the same concurrency. So what's wrong with this? What's wrong with this from my perspective is that we didn't get the total future. The final future of this workflow didn't happen till down here after we'd already completed running first. And I'll show you in a second why that's bad. So say I stick the 2 code examples above into a function. So total first, that's going to return a future. And I could pass that into total again. So we're going to end up calling first 4 times. Whoop. Hold on a sec. Right, the other way I can do it. Oh, yeah, there we go. So it's going to run 4 firsts, 2 in here, 2 in here. And then it's going to run 3 totals to sum them all up. And notice that the 4 firsts ran at the same time. If I do it in the other style here, where I call first, wait for the results, and total them, it's not going to perform quite as well. We're going to run 2 firsts and a sum, and then we're going to run the next 2 firsts. So what's happened is, in this example, we get a future back straight away. Nothing delays the final future being returned here, which means we can feed it straight into this app invocation, which means we can move on to evaluating this and getting the future for this as well. Okay, so what I claim is that if you're trying to build any kind of modular workflow using functions or anything like that, calling .result anywhere in your code apart from at the very end is a very bad thing to do. Okay, so like I said, .result is your enemy because it really stops the ability to make modular workflows that can be built out of Python functions. All right. So I'm going to do a slightly more complicated example now, which talks about assembling a graph much more dynamically. And I'm going to build a fantasy sports league game. So in the fantasy sports league game, we've got a number of players, and each player will be analyzed based on perhaps their match history over the last year or so. And then we're going to have some teams, and when you play fantasy sports league, you get to pick which players you want to have in your team. So because it's a fantasy sports league, different teams can have the same player. So for example, Doughnut appears in 3 teams and Butch appears in 2 teams. So I'm going to take all that analysis of how you're going to analyze a player, and I'm going to not look at their history. All I'm going to do is say their goodness score is just the length of their name. Okay, so I put some logs in and some delays in to make it seem a bit more interesting. But if I run that now, we're going to analyze Abi, who's a sumo wrestler, I think, and he scores 3 because that's the length of his name. If I was to score Butch, he would score 5. Okay, so the next obvious thing to do is we're going to analyze all of those players. So what I'm going to do is call analyze player on every element in the list of players, and this is going to return a future. And what I'm going to do with that future is stick it into a dictionary, into a Python dictionary, keyed by the name of the player. So if I was to run this, there's no dot result in here. If I run this, or when I run this like this, straight away I get back a Python dictionary with each player and a future that will eventually hold their result. And if we scroll down slowly over time, the computations are completed. Okay, so we never called dot result. We got back a future really fast for each of the players. So I have this dictionary, and now I'm going to use that in a slightly more interesting way. I've got the teams defined. You're allowed to have 3 players in your team. So team A is Dugnut, Bannister, and Ennis Hill. And if this was a real fantasy sports league, I'd take all the player analysis for the 3 players and combine them together in some fancy sports science way. What I'm going to do here is just total up the 3 scores of the 3 players. Okay, so for each team, there's the team name and the list of players, and I'm going to invoke first I'm going to create a list of the relevant player score futures. So this data structure up here, I'm going to index in and grab the future for each one. So what I'm going to end up here is a list of three futures that are the 3 futures for each team member for their score. And then I'm going to invoke total on that list. And then I'm going to stick the final results in a final results list and return that. So that lets me have, I should run that. So here's my complete workflow. We're going to analyze all the players. That's going to launch a whole load of tasks and return a dictionary. And then I'm going to pass that dictionary into analyze teams, which is going to return a list of results. And then below, I'll be able to print the scores for those teams. So if I run it, okay, what happens straight away, we started analysis of each player. We straight away can prepare the teams, and we straight away get to this all teams prepared message, which happens at the end of the workflow. So we've told Parcel the entire workflow, the entire graph, without having to wait for any intermediate results, using this dependency list that was dynamically assembled. And then as time passes, you can see each totaling appears when we're done with one particular team. So as soon as we've done Abby, Butch, and Dugnut, which is this team, team B, we can straight away move on to the team combination sum total. Okay. And to prove it worked, whoops. Oh no. Oh, it's because I set it running again. Hold on. There we go. Okay, so the point of this is that it's good if you can return your futures straight away as soon as you can. It really lets you make these modular workflows that don't interfere with each other's concurrency. If any of these two functions were calling dot results, they would mess up concurrency and processing for other bits of the workflow. So that's calling dot result isn't really a local operation as far as Parcel is concerned. It globally stops stuff happening. Other things that are interesting, I'm just going to run this again because I like the output. Other things that are interesting is that we can get better concurrency because we're able to run this total operation as soon as the relevant teams are prepared. One sort of simpler way of implementing this would be to process all the players and then wait for all the players to finish, and then process all the teams and wait for all the teams to finish. And what that would mean is that we couldn't interleave the totals here and the player analysis. So if you had a lot of workers, that might result in 1,000 workers that slowly have to drain of work entirely before you can move on to the next step. Using these much more focused dependencies lets you start running jobs earlier to make use of those workers that would otherwise be idle. The other thing that's interesting is if there were exceptions here. So if an analysis for a particular player failed, we would still be able to do the team calculation for every team that didn't use that player. So if, for example, Bannister, the player analysis for Bannister had failed, we would still have been able to do these two team analysis totals. So it's still, in many workflows, very useful to get partial outputs. In the LSST example that this is based on, it would mean that we would have been able to cover large chunks of the sky with just a few holes in the sky where things had failed. Okay. So I'm going to introduce a new feature that isn't in Parcel 1.00 and it isn't in Parcel Master, but I'm working on getting it merged. It needs a bit of tidying up. And that's a new application type called a join app, which is a cross between a Python function and a Python app, a Parcel Python app. So like a Python function that I called above, it runs in the submitting process. Like a Python app, it can launch other apps. But what it's able to do is wait for dependencies, and it's able to have a look inside and see what those dependencies are, which is something that you can't do with a regular Python function. So here's an example computation that is the Fibonacci sequence. It's recursive. Join apps don't have to be recursive. It just happens to be this way with the Fibonacci sequence. So I'm going to define this. So this is the bit of code that won't work if you try and run against Parcel Master now, because a join app doesn't exist. I'm going to say if you call Fibonacci with a value n, then we just return a sum of 0 objects, which is 0 if you ask for the 0th element. If you ask for the first element, return a total of 1. And if you want a different number, then we add these two Fibonacci recursive calls. So this app is deciding which other apps it wants to run as it runs, which is not something you can really do with Python apps. Okay, so if I call it with 0, it runs almost you can imagine it a bit like a sub workflow, vaguely. Runs a sub workflow in these two cases with 1 extra task. If you run it with a different number, it runs a sub workflow with many other tasks hidden inside here. And what you return, instead of returning a value from a join app, what you return is a future. That is the future that says our sub workflow is done. So Fib3, if I run it, you can see it runs 5 totals, returns 2. I'll show here if we have this app. So if we're going to make an app which needs to make this decision, this if decision, based on the results of an earlier step. So instead of saying Fibonacci 3, I'm going to say Fibonacci and pass in a future from an earlier workflow step. So when I make this invocation, Fibonacci doesn't have a number to make this decision. Okay, it's going to have to make that decision later on, which is something you can do with apps, but you can't do with Python functions. So if I run that, it's going to be a bit of an explosion because first returns 10. So Fib10 is a lot of recursive calls. But if I do this, it's going to wait 5 seconds for the result. And then bang, there's all the recursive calls happened. And at the very bottom, I should have the output 55. Okay, so the big deal here is that the use case we have in LSST is you want to kind of package up a little workflow which is going to change what it does based on the results of a previous step. Okay, so packaging up that little sub workflow as a just as a regular Python function isn't quite good enough, because we need parcel dependency handling. Okay, so that's a new feature that won't work if you try it now. There's a link if you want to try it to the pull request. Yeah. And then the last bit I'm going to talk about is raw future objects. So parcel apps return app futures, and app futures are just instances. They're a subclass of standard Python implementation of futures in concurrent.futures. So I think Yadu's talk tomorrow, he's going to use these as well. So they're quite tangled in the guts of Parcel, and they're used everywhere. So what I can do is just make a future like this. Oops, let's import it first. Okay, there's my future, and nothing's going to happen. So when you get an app future back from invoking a Parcel function, you get the future back, but Parcel is also going off to run the code that's going to put a value in that future eventually. What I've done here is just made a future. There's no way this is ever going to get a value at the moment. It's just going to sit there forever. Okay. And I can use any future as a Parcel dependency. It doesn't have to be from an app invocation. So I can invoke total here. I'm going to add 1 to whatever value is going to come out of that future. Okay. So this future hasn't come from an app invocation. I just made it there. And if I do that, there's my app future. It's in pending states. If I ask if they're done, nope, they're both not done. And they're just going to stay like this forever. This future is never going to complete because there's no mechanism to make it happen. And total is never going to complete because it's going to be waiting for this future forever until I call the standard future method to put a value in. So I can set the result of f to 10. And immediately the total app runs because this got a value suddenly, which meant this was unlocked for dependencies. And I can get the result, which should be 11. And there we go. Okay, so that's a little bit of a view into the guts of what's happening with dependencies in Parcel. And one place I've used that is in playing with different dependency behavior. So join apps I originally prototyped by just hacking together a future like this to try and get the semantics I wanted and the behavior I wanted. So what I'm going to show now is another future that I want for LSST. And that is, I would like my apps to see when their dependencies failed. So normally in Parcel, if I have an app with a dependency, if that dependency fails, my app doesn't even run ever. It just, it fails with a dependency exception straight away. So we're not trying to run code on values that don't exist. But we have a case in LSST where I would like my app to be able to see that some of its dependencies failed and decide that actually this is fine. I can still run with only some of my dependencies being successful. So what I'll do here, here's my app that's going to be successful. It returns a random number. Here's an app which will always fail, called fail, and it will just raise a runtime error. Here's an app that's going to compute the average of its arguments. So you pass in an argument list, we accumulate the number and the total and divide one by the other. So if I take the average of 50 and 60, it's 55, and there were 2 results. That's a pretty straightforward mean. Okay. So I can run it like this, 4-node workflow, run rand 3 times, run average, and I'll get a number. So we counted 3 results, which you would expect, 1, 2, and 3. Average is about a half. That's what you would expect. But if I run it like this, my 3 inputs are rand, a failure, and rand. If I run that, it's going to be quite an ugly stack trace. But what you get is a dependency error. So average never ran at all. Okay, these rands probably did run, but then we just ignored their results. Okay, because this failing caused everything downstream of it to fail. So what I would like is for average to know if it's got a failure or not. So I'm going to make this subclass of future called exception hiding future. When you construct it, you pass in a parent future, and I'm going to say when the parent future gets a result, when it's done, I want to call this callback. And this callback can do two things. It can say if the parent got an exception, I'm going to, instead of keeping that exception, I'm going to discard it and set the result to lol. And if I got a normal result, then I'm just going to set my result to that result. So for example, so if I don't use this adapter future and I do this, I'm going to get a stack trace. Okay. And there's the demo exception that we ran here. Okay. If I run this with the exception hiding future, I'm going to create the future, wrap it in my new prototype, and then set an exception. Oops. Oh, hold on a minute. Let's actually define it. Here. If I do that, then it doesn't throw an exception anymore. That exception's been hidden and replaced with the string lol. If I just pass in a normal result 3, I still get my normal result 3 back. Okay, so I'm going to tweak average a bit to check if the argument it's given is a string or not. So if it's a string, I'm going to ignore it as an error. And otherwise I'm going to accumulate it. So now I call average. I'm going to call rand, fail, and rand. I'm going to wrap them in this exception hiding future and pass that into average. And what's going to happen is I get back an average. Okay, you can see that only 2 results were summed. So average was able to make this decision here that it could see that one of its arguments failed, and it gave us the average. So that's been something that I wasn't expecting to be useful, but it was something in LSST that's been very useful for prototyping interesting dependency behavior that isn't Parcel's standard model, without having to be really invasive into the core Parcel code until I was convinced it would be useful. Okay, so that's pretty much the end of everything I have to go through. Like I said, this notebook's already linked on the program. There's a little bit more down at the bottom if you want to read, but that's me done.